horizontal stretches and compressions. I have a function here from trigonometry, this sine function, and I've chosen to use this one because I think it's easier to see stretches and compressions using this particular function since it kind of looks like a spring. So here's a sine function. You'll notice the x-axis has multiples of pi because it's kind of inherent towards this particular function. So I'm going to go here and type the following. So I'm going to multiply that x by 2x. And it produces this function right here, the blue function. And you'll notice now that I just, like I did for the horizontal shifts, I want to keep track of what happens to particular points. So consider this point right here, this pi comma 0. When I did this new function by taking x and multiplying by 2, where does this point go? So when I trace, I see that this graph that's, I don't know, call that red, sort of a light red color, does this particular move, notice up and down. Where is this move in the blue function? Well, look right here, this is going up and back down, and looks like there it is, pi over 2. 0 is where this new point is located. There's where it used to be, now there's where it's at. And the curious thing is that the x value has now changed from pi to pi over 2, which is a reciprocal of 2. So it looks like by multiplying by 2, I've actually taken the x value of pi and divided it by 2. So now it's pi divided by 2. So why is this happening? Same thing as before, we need to keep track of my y values. It's all about the y values. So this one's going to feel a little strange because we cannot really do the calculation like I did earlier. But here the way this works. Right now, the sine function, I enter pi and I get 0 back out. And if I use the function the other function notation, it's this. Okay, so that's it. So I have my x, my y, I enter this pi, and I get 0 back out. The question is, how does this new function work? And in this new function, I'm entering now twice x, and I get this g of x. Oops, not that. And I get y out. But again, think of it this way. I don't want to change the y value. And the question now becomes, what do I enter here so that I get 0 back out? Well, I know when I enter pi in sine, I get 0. Now I want to enter a number so that I get pi. So the idea is, what do I enter here so that I get pi? So sine of 0, sine of pi gives me 0. Well, it appears that if I entered this, pi over 2, that would do the following. Pi over 2, 2 divided by 2 is 0, that gives me pi, sine of pi is 0. And that's exactly what you see it's happening here. Now, this point that used to be here has now moved over here. When I enter pi over 2 into this function, I all of a sudden get 0 back out. So it's really all about the y value, keeping the y value. What is it that you need to enter now to get that same y value back out? Now, what people, of course, your intuition says, because I multiplied by 2, this point should be now twice as far. It should be over here, 2 pi, right? But it's not. Think of it now in this manner. When you enter values, the 2 is speeding up the entire process. It's getting faster to get the same y value to pop out. So the result is this 2 is speeding everything up. Every x value now is being multiplied by 2. The output staying the same, but this is speeding things up. So the result is the graph compresses by a half. In order to get the same values, you don't need to enter a big number. Before, you needed to enter pi to get 0. Now, because everything is being speeded up, you only need to enter pi over 2. So think of this 2 as speeding things up. It's like running faster. So you don't need to enter as big of a number to get that same output to come out. And the result is, visually, is that the graph compresses. And again, just to, I go g of, and again I put a 2, but I enter pi divided by 2. What do I get? I'll get the 0 coming out. Note, that's all I need to get that 0 to come out. So let's try a different one. What if I were to do the following? G of half of x. Now this does the exact opposite. So I'm going to remove the blue. I'm going to remove. So what happened to pi over 2? Well, it looks like the graph, when I multiplied it by a half, has stretched. So this point that used to be here, notice how this moves up and down, hitting the 0. Now it takes twice as long to hit that 0. There's the up and down again. So multiplying by a half has, instead of what you would think would happen is that it would compress, but no, it actually stretches it out. Why? Because now everything is slowed down. I need to enter a bigger x value to get that same value back out. So the half means it's just going half as, whatever you entered is only worth half as much. Before, whatever you entered is now double. You're getting more out of it. So the effect is that it compresses. But now you enter anything here, you're only getting half the value. So it's going to take twice as much to get to the old value of 0. So that's exactly what's happening. That point, pi over 2, has now been moved to, instead of cutting it in half, it now takes twice as long. If I use the same reasoning as before, again, pi used to give me 0, so what happens now when I consider half of x, y, and I still want that same output of 0, well, what do I need to enter here to really, think of it this way, give me pi back out? When I compute it here, as soon as I get pi to come out of that calculation, the function will give me 0. Well, it looks like if I'm multiplying this thing by a half, I need to enter 2 pi. So when I come over here, I enter 2 pi, and indeed that gives me pi, which produces the 0. So that's why this point is way over here now. It's just going to take you twice as long to get to that same value, that same output. So again, multiplying by a half slows everything down, which in turns in the graph, it stretches it because it's going to take more to give you to that same point, that same y value. Okay, so hopefully, again, that helps out quite a bit. And again, the sleight of hand things is, that's not the way you would see it. All of a sudden, when you would see the function, it would look something like this. And expressed this way, the transformation is, it's not as apparent, but you have to understand that this is your parent function. And when you see that above, you realize the transformation has taken place. Now, of course, this function notation that you see here, this is actually is function notation, so you kind of get to see what it really is. For this particular type of function, the transformation really doesn't go away. You can see it just sitting right here. So you see this, and I realize, oh, that's my parent function. If I see something like that, I see, oh, it's a shift, a horizontal shift of this parent function. So for this particular type of function, the transformation piece actually does not go away. You can actually see it either stretching or compressing.